Hi all. I'm re-recording the Math 70 lecture because I made a mistake on uploading it. So I'm going to go through all the asymptote stuff again. I'm going to use the same examples. Might even be a little more organized the second time. So let me share my screen with you. It'll be the same problems we were looking at, but it might be a little bit different order. So let me just bring it up and we'll talk about it. So I'm having a meeting with myself. All right, so we're talking about asymptotes, and we talked about them yesterday and about how to find asymptotes for particular functions. And those rules you'll find in the lecture from yesterday or the day before yesterday. In particular, we talked about vertical asymptotes and horizontal asymptotes. And on any problem, such as this first one here, you want to start with finding the domain. And what you see here is that x can't be 2 because the denominator can't be 0. So the domain is minus infinity to 2, union 2 to infinity. The nice thing about finding the domain first is that tells you virtually it tells you exactly where the asymptotes are. Unless there's something up here to be canceled out, if something cancels out as a whole, if it doesn't, or if you got it in this completely reduced form, you can just read off and those will be the vertical asymptotes, okay? The horizontal asymptotes, there were 3 rules. These are listed in your book pretty clearly. If you have a rational function like this, one polynomial over another polynomial, if the power in the numerator is higher than the power in the denominator on the highest power term, then we don't have a horizontal asymptote. If the powers such as in this one, the highest power on this one is x to the first, highest power on that one is x to the first, then you just read off the coefficients from there, and y equal to that. In this case, y equal to 1 over 1 or 1 would be the horizontal asymptote. Finally, if you have a power in the denominator that's higher than the power in the numerator on the highest power term, then you'll have an asymptote horizontal of y equals 0, because the bottom with a higher power is sort of overpowering the numerator, and the fractions really getting smaller and smaller. Okay. So so what happens there is that you can easily see what the horizontal and vertical asymptotes are, and there are lots of problems in the book. So I encourage you to look at the homework. Another thing we might do is find one of the intercepts. Usually the y-intercept's easy to find. If you just let x equal 0, you'll wind up with minus 3 over minus 2 here, and that's just 0 3/2. Okay. So that tells us some general things about the function just by looking at the function itself. Now let's look at what the derivative tells us. If you want to take the derivative of this thing, the first derivative, we're going to use the quotient rule. It's bottom x minus 2 times the derivative of the top, which will be 1, minus the top times the derivative of the bottom, which is 1, over the bottom squared, or the denominator squared. When I play this out and play that negative through there, you'll wind up with 3 minus 2, which is 1. The x's will cancel out, and you get 1 over x minus 2 squared. So that is the first derivative. The second derivative is done by a technique we have not done, but I'm going to tell you that it's minus 2 over x minus 3 squared. Now, what we're going to look at is what the first derivative tells us first. So I'm going to look at this right here and draw my number line. The first derivative is going to tell us about increasing, decreasing, and possibly local maxes and local mins. You need to find the critical numbers, but the interesting thing about this function is that the only way this derivative can be 0, which is how you find the critical numbers, is if the numerator is 0. Well, the numerator doesn't have any chance for change, it's 1. Okay, so it's never going to be 0 there. So what we're going to do, there are no critical numbers, but we do have this asymptote, all right, at x equal 2, and things can happen around asymptotes, so that's the only thing we're going to put on there. this asymptote. So if you look at then the rest of it, what we're going to do is test left and right here in the first derivative, and it'll tell us increasing and decreasing. So if I plug 3 in, for example, I'll get 1 over 3 minus 2, which is a positive number squared. So 1 over a positive number is going to be positive. That tells me it is increasing there. To the left, if you plug in a minus 1 or a 0, it doesn't matter, anything to the left of 2, you're still, when you put it in this bottom part, you're still going to get a negative number, but then you square it, so it'll still be positive. So 1 over positive is a positive. So that says it's increasing. If we write that in interval notation, it's minus infinity to 2, union 2 to infinity. 2 to infinity is where it's increasing. It's not decreasing anywhere. Okay, it's decreasing nowhere. So there's no local max or local min, because to have one of those, you have to have, it has to change from being increasing to decreasing, so that you either have a hill or vice versa, you'd have a valley. So I'm going to go on to the second derivative and see what happens in the second derivative. The second derivative tells me about concavity. And in terms of concavity, I don't have any places where the second derivative is 0, because again, that numerator doesn't have any chance of being 0. It's minus 2. So what I'm going to plug in here, what I'm going to do here again, is put the asymptote on there, because things can change around an asymptote. Even though it's not an actual point on the graph, things can change on either side of it. So if I plugged in a big number bigger than 2 over here on the right, then if I plugged in 4 minus 3 is 1 cubed, that's positive. Minus 2 over a positive number will be not minus. So that tells me there I have concave down, because I get a negative second derivative. Concave down, it dumps water, okay? To the left of 2, say at 1, 1 minus 3 would be minus 2. Minus 2 cubed is minus 8. Minus over a minus there is going to be plus. So that says on that side it's concave up. Okay. So I've taken there are no inflection points. Even though the concavity does change, it's changing at an asymptote. So there's no actual point where the concavity changes, because we know we'd have no point along that asymptote. You cannot cross a vertical asymptote. So the next thing I'm going to do is do my master line. And that'll look like this. It'll have a 2 on it for my vertical asymptote. And to the right of 2, I have increasing and concave down. So increasing and concave down. The increasing from right here, all right, increasing right there. So increasing and concave down. I'll put that on there. It's increasing, concave down. To the left, I'll have increasing, left of 2, and concave up. So I'll increasing, concave up. Now all I really need to do is look at what those shapes are. And those shapes, if we look at those things, remember that increasing goes up, increasing concave down goes up and is bowed downward. Increasing concave up still goes up, but it's bowed upward. Now, the question here then is, excuse me, I keep bouncing all around here. The question here then is, where can these pieces fit? Well, the piece right here, the only way it can do what it needs to do around the asymptote is to be fit right in here, because it's got to get closer and closer to the horizontal, and it's got to drop out in the other direction. Sorry about that. The other one, increasing concave up, it has to get closer to the vertical asymptote, and it has to tail off towards the end to minus infinity. The only way that thing can fit in there is fit in that. So the asymptotes kind of hug what the graph looks like there. And that's what the graph of that one looks like. So that's how we look at asymptotes. You just have to be careful to get the asymptotes on there properly and find the increasing and decreasing properly. Okay. I did not do this one. I'm going to do this one later. So I had it written up, but I didn't do it. The one that and we did this the other day where we matched these functions with their proper pictures. I'll talk about that again. If you want to find out the horizontal asymptote on this one, since the power in the numerator, the highest power in the numerator and the highest power in the denominator is exactly the same. The coefficients on those things are 3 and 1. So y equal 3 over 1 is the asymptote. So you can see up here, when you look at the pictures, the only one with that asymptote is D. So that's the answer to that one. This one, the power in the numerator is less than the power in the denominator. The highest power is less than the highest power here. That means the denominator just keeps getting bigger and bigger relative to the numerator, which means we're getting a smaller and smaller fraction, which means y is 0. The only one that has, in this picture up here, an asymptote of 0 is B. So that got matched with B. In order to find asymptotes, horizontal asymptotes, and vertical ones, it makes it easier. You will need to find a common denominator, which is what I did here. And if you look at this one, the highest power in the numerator is a 4. Highest power in the denominator is a 4. The coefficients are 2 over 1. So what you wind up with is an asymptote of y equal 2. And if you look at the picture above, the only one with the asymptote of y over 2 is A. In 4, I did the same thing. I found the common denominator. After doing that, power in the numerator is the same as the power in the denominator when you look at the highest powers. That says that we pick off the coefficients. Y equal 5 is going to be the asymptote there. This is the horizontal asymptote now. And y equal 5, the only one where we had an asymptote of y equal 5 was C. So that one got matched with C. Okay. The other problem I did today was a little harder problem. And I gave you the function, I gave you the first derivative, I gave you the second derivative. All we're going to be asked to do here is to analyze these things. We've already got the derivatives all taken. We just need to analyze those derivatives. So what I have at this point then is the function right here. Let's see, get a different color on that. The function itself is right there. First thing I want to do is find the domain. If you factor the numerator, you'll see the denominator, sorry, you'll see that the denominator cannot be 3 and cannot be minus 3 because that would make it 0. So my domain here bumps out 3 and minus 3. It goes from minus infinity to minus 3, union minus 3 to 3, union 3 to infinity. And the parentheses bump out the minus 3 here and the 3. If I think about horizontal and vertical asymptotes, remember that the domain really told you where the vertical asymptotes were. So the places where the denominator was 0 is if this is in a reduced form, which there's nothing you can cancel out there because x squared plus 1 won't factor, then x equal 3 and x equal minus 3 are vertical asymptotes. They were the very places you had to dump out of the domain. And the highest power in the numerator is the same as the highest power in the denominator. So the coefficients on that are 1 and 1. So y equal 1 over 1, or just 1, is the horizontal asymptote. So I have 2 verticals here and 1 horizontal. Okay, so what does the first derivative tell me? So I'm going to go on to talking about the first derivative. Here's the first derivative, right here. Looks like that. So now I'm dealing with that. The first derivative, again, I draw a number line. I look for critical numbers and I put the asymptotes on. We know the asymptotes are x equal 3 and x equal minus 3. So we put that on. The only way we can get a critical number out of this is if the derivative is 0. The only way the derivative is going to be 0 is if the numerator is 0. And the numerator is going to be 0 at 0. So that's our critical number. I'm going to put that on here. Again, I put the asymptotes on there and I put 0. Once I get that done, all I have to do is do some testing in these intervals. So you remember, if you're finding increasing or decreasing, you test in the first derivative. So to the right of 3, say 4. Minus 20 times 4 will be minus 80. No matter what I plug into this thing, I'll get 4. If I plug in 4, I'll get 16 minus 9 is 7. It gets squared. This thing's always going to be positive. I don't really need to worry about too much there. The positive is not going to change a sign. So it all depends on the numerator. So I plug in a 4 and I get minus 80. That means it's going to be decreasing in the first, to the right of 3. Between 0 and 3, if I plug in 1, minus 20 times 1 is also minus. This is always positive. So what I get there is a minus. So that means decreasing there. Between minus 3 and 0, say at minus 1. If I plugged in minus 1 here, right there into the first derivative, minus 20 times minus 1 will be positive over something that's always positive. So that'll be positive. That thing in there, that's positive. And finally, to the left of minus 3, if I plug in minus 4 to the first derivative, I'll get something squared, which is always positive. And minus 20 times minus 4 is positive. So I get positives there. So where I get positives, it's increasing. So going up, decreasing, or where I get negatives, going down. Remember, the first derivative also tells me not only increasing and decreasing, which I'll state like this in interval notation. Notice from minus infinity to minus 3, it's increasing. Then from minus 3 to 0. You don't want to include an asymptote. An asymptote is a problematic point, a spot in the function. So you just don't want to skip merrily over that. Just do it in 2 separate pieces. It's decreasing from 0 to 3 and from 3 to infinity. Again, don't do all of this from 0 to infinity, because you've got a really problematic spot there at 3. First derivative tells you something else. It tells you local maxes and local mins. If you look at this, the only possibility for a local max or a local min, remember, is where it changes from increasing to decreasing or vice versa. Here we get going up on the left, going down on the right. That means we're going to have a local max at x equals 0. If you want to find out what it is, you go back to the original function. That's how you found a point. You plug in 0 here. 0 squared plus 1 is 1. 0 squared minus 9 is minus 9. I get minus 1/9. So out of that, when I graph this thing, I'll have the point 0 minus 1/9 to put on the graph. All right, next thing we're going to do is concavity. We use the second derivative for concavity. There's my second derivative. Okay. Notice here that it's still going to have the problematic points at 3 and minus 3. Those are where the asymptotes were. This will always be positive. X squared plus 3 is never negative. If you square x squared, the very least you could get would be 0. If you add 3, you're always going to get something that's at least 3. And something that's positive times 60, which will be positive. So this number up here in the second derivative will always be positive. So this thing is going to change signs depending on this cube here. Now, a cube is not always positive. So that's what we need to test next. So I draw the line. I put the asymptotes on it. I have no places where the second derivative is 0, so I don't have anything else on here. And then I test in these sections. So if x is bigger than 3, say at 4, I'll have positive up here, these 60 times whatever, it's 19. Doesn't matter, that's always positive. If I plug in 4 here, it'll be 16 minus 9, which is 7. A positive number cubed is a positive number. So I have positives in the second derivative for x is to the right of 3. Positives mean concave up. Between -3 and 3, I wind up with testing maybe 0. That would make this 60 times 3, 180. If I test 0 here, -9 cubed. Well, a number times itself, a negative number times itself 3 times is going to be negative. That tells me it's concave down in between -3 and 3. Finally, if I pick a test point to the left of -3, say -4, this is always positive. -4 squared is 16, -4 is 7, right? And 7 cubed is positive, so I get a positive over a positive. Down here, it's concave up, okay? So now, what I want to do at this point is put these two lines together on what I call my master line. Nice if you just sort of line them up, one right under the other, guys, and you can see sort of what happens in all these intervals. So for example, if I said, I now want to look at what happened with all of these things in all those intervals, I'll just say my master line has a asymptote on it. I'm going to put, on my master line, I'm going to put my asymptotes and the critical number that came from the first derivative. And then I'll look to see what happens in every interval. So to the right of 3, I had decreasing and concave up. So over here in the right of 3, I put decreasing, concave up. Between 0 and 3, right here, it was decreasing, but it was concave down. So decreasing, concave down. Between -3 and 0, we had increasing here and concave down still in there. So that's increasing, concave down. Finally, to the left of -3, I had increasing. It's over there to the left of -3. I had concave up. So this is increasing, concave up. Okay, now you can see it because I left it written down here, but these are the 4 possible shapes you can get, aside from a straight line is the 5th one. But when we have concave up, decreasing, I'm just going to kind of trace over it here, guys. Concave up, decreasing, we've got a shape that takes my pen down for decreasing, concave up, it's bowed upwards. That's what concave up, decreasing looks like. Concave down, decreasing means my pen goes down, but it dumps water. All right, it's bowed downward. Increasing means my pen comes up. Concave down means bowed downward, so I get something like that. Increasing concave up means my pen's coming up. See what I can do with the cursor here, the cursor's coming up. These are both increasing. Cursor's coming up, cursor's coming up. On these, cursor's going down, cursor's going down. This one's increasing and it's bowed upward because it's concave up. These are the shapes that have to fit into this picture here. Now remember, I drew the picture to begin with. Actually, I'm going to dump this for just a second. Okay, the picture that I drew to begin with, what I wanted in that was just the asymptotes. And what I'm going to do now is fit these shapes into those asymptotes. So, so if you look at this one, that's the one to the right of 3. It's got to get closer and closer to the horizontal asymptote as we go out to infinity. So we're going out to infinity in that way. That's the x values. And as it goes near the asymptote, it shoots either up or down. This case, if it's on the left of that asymptote and it's going up, so it's got to shoot up. So I've got to kind of draw it like we know they behave around asymptotes. In a way, it gets kind of cradled by the asymptotes there. Now, right here, if you look at these two together, what we knew is that we had a local max at 0, and it was -1/9. I'm going to go ahead and put that point on there That's one thing we already knew. That's the only real point we looked at. At that point is a local max. So you know that's a peak there. So what happens on the right, it's shaped like this. That makes sense. Because it's got to go down. It's getting closer and closer to the asymptote. This side right there is going to head in the same direction as that one. If I go from left to right, it was increasing and then it was decreasing here. So that second piece of that looks like that. Finally, this piece right here has to increase and be concave up. It has to get closer to the horizontal asymptote as we go to minus infinity. And it has to get closer to the asymptote shooting up infinitely or minus infinite to minus infinity. To put that in there and make it do both those things, it has to be there. It could not be down here because you could not get it closer and closer to the horizontal asymptote if you drew it, if you tried to draw that shape down here. So that's the final graph on this one. And that's what we talked about today. Putting all these graphing things you know together. First derivative tells you about, function tells you about domain and horizontal asymptotes and vertical asymptotes. You can get points from that. The derivative tells you about increasing and decreasing and local maxes and local mins. The second derivative tells you about concavity. Okay, I think that'll do it. I think that's all that I did in class today. Sorry that I messed up the video, but everybody should have what they need here, and I'll talk to you on Monday.